In this video, I will do an oversimplified explanation of what constraint random is. At the end of this video, you should understand the concepts of stimuli generation in digital hardware verification, as well as metric collection and digital IC project closure. System Verilog inherits the Verilog language, as well as providing object-oriented programming capabilities on top of it. Together with these object-oriented concepts, verification-specific constructs are also available, like assertions and coverage. Coverage is a metric collection tool used for recording and measuring events, variables, and parameters. The first step of a verification project is to instantiate the RTL, called DUT in the scope of verification, which is short for Design Under Test. During the instantiation, we connect different signals to the inputs of the DUT. These signals can be standalone signals or part of an interface. A standalone signal is usually controlled from the module where the DUT is instantiated. Interfaces, however, can be wrapped in virtual interface objects specific to the System Verilog language and passed over to the test bench's object-oriented infrastructure, where the signals from the interface can be controlled. UVM provides a simple database for this, called UVM config database, which is available globally and can store any kind of data type. Starting from the basics of Verilog, a signal, either standalone or part of an interface, can be toggled directly in an initial block or by using a task. You can see in the example what happens when we simulate a simple code block like the one displayed. However, this is inefficient, so the next logical step would be to organize stimuli in transactions. We want to reach a higher level of abstractions that would ease our work and allow us to think in terms of basic software. In the example on the screen, you can see a basic task that randomizes the data and the delay and then generates a transaction followed by said delay. This task is then called multiple times, resulting in the waves displayed. We are going to see in the next slides that constraint random verification is actually used to serve the purpose of abstraction and verification space exploration. We need to continuously move to higher levels of abstractions once the lower layers of control are proven to be working. For this goal, UVM provides a hierarchy of classes starting from the most basic item, which encapsulates the transaction that goes on the bus, up to the test case that contains the intent of the simulation. In between the test case and the item are a collection of hierarchical sequences that offer different levels of abstractions. These sequences are meant to be randomizable, reusable, and controllable by all entities above them in the hierarchy. As an example, we are going to oversimplify this by removing the in-between layers of control and work with just one layer of sequences. We can see in the first picture on the slide the task drive item, which exists in a component named driver, and that puts the item on the bus. This item is created and randomized inside sequences, action that is portrayed in the bottom left picture. Please note that the fields in the item on the left are constrained based on the fields in the sequence, which are on the right. The fields in the sequence have a higher level of abstraction, portraying the boundaries in which the item fields can be randomized. Furthermore, you can see on the right picture that those boundaries are controlled from the test case, based on the type of scenario that we want to create. The intent of the test case is propagated through constraints, from test case to sequences, and finally to items. Going a bit more in depth into what constraints are, we can see now on the screen the basic constraints of the item. Most of the time, these constraints are there to assure that all generated items are legal transactions, and optionally that they fall in line with what a realistic traffic pattern would look like. Furthermore, we can see the constraints of the sequence. Bear in mind that these constraints take effect on top of the ones in the item when randomization finally occurs. Finally, the sequence is created and randomized in the test case, where the constraint propagation originates from. In a typical test case, the driver works with a basic item. Adjustments to the constraints can be done by extending the item, but at core, the item tends to be singular. Sequences and test cases, however, are part of a collection created to serve the purposes of verification and to reach a variety of scenarios. On top of those different sequences that can be implemented, the behavior can also be vastly different based on the constraints applied. This is one of the most powerful features of constrained random verification. By applying different constraints on the same sequences, a large variety of scenarios can be simulated using the same testbench infrastructure. Now that we covered stimuli generation part, we are moving on to the checking part. Checking can be represented by a variety of assertions. Some can be temporal assertions located directly in the top module or in the interfaces, as depicted in the top picture. Or there can be static assertions applied on an event based that check transactions, like in the button picture. The event that triggers the scoreboard check task is a write to the data out FIFO, which coincides with the transaction going out of the RTL. The check will be a comparison between input transactions, which are stored when a transaction is recorded on the input of the RTL, and the output one received from the data out FIFO. The relationship between the input and output will be handled by the compare items function. The final piece of the puzzle are the metrics. For this purpose, we define coverage as seen in the two pictures on the screen. In the example shown, the covered metrics are parameters of the input and output transactions. These are not the only metrics that can be collected. Any number of events, parameters, fields, or configuration values from both the RTL as well as the testbench can be recorded using coverage. The coverage collected can be mapped to a vPlan and evaluated using the preferred vendor tools. This shows us what scenarios has been exercised and what is left to be covered, giving us a comprehensive view of what randomization space has been explored. Having a bird's eye view of the testbench allows us to put the notions we talked about in perspective. The DUT with its interfaces is in the middle, and those interfaces are driven and monitored by protocol-specific UVCs. UVC means a universal verification component. The monitored stimuli recorded by these UVCs are passed through ports to the scoreboard, which does the checking, and the coverage collector, which records the metrics. This is how all of the concepts discussed fit in the bigger picture. Finally, we will have a sneak peek at the flow of verification in a live project. What is not shown in the picture is the initial design phase and the vPlan development. That happens before any coding starts, for the verification team. After that, the first phase of verification covers the first drop of the RTL, which includes the connection of the DUT to the testbench and the first smoke tests with visual inspection of the results. The second phase includes the development of checkers and partial coverage. The third phase, and the most lengthy, is the completion of all coverage as well as any missing or newly discovered needs for checkers. There is also a continuous loop of debugging and analyzing of the metrics. The final phase is the analysis together with the designer of any holes in the verification, which leads to either the development of specific directed test cases or necessary coverage waivers. When the coverage is filled up and the passing rate is 100%, then the project is complete. Let's try to summarize what we learned today. We started from basic Verilog info of how signals are driven, and we've advanced that to a higher level of abstraction by using transactions. We've put the notion of abstraction in context of a verification environment. We've discussed the notion of randomization and its different layers of constraints that shape scenarios. We've discussed about checkers and trigger points. We've discussed metrics and how coverage is defined and evaluated. And for the final piece, we've had a look from above at the verification environment architecture, as well as the steps of a digital IC development. The information presented here is by no means aimed at making you an expert on these topics, but to give you a bit of context for the concepts used in digital verification. If you want to find more information on any of the discussed topics, check our other videos. There are many other in-depth presentations and even workshops with code examples. I am Andrei. We are Amic Consulting. We provide services for verification in a variety of areas like computing, automotive, servers, telecom, and others. You can visit our website at the link on the screen, and if you are there, you might as well visit our brothers and sisters at Amic EDA. That's all for now. Thank you for watching.